more thing, it seems that your batch doesn't get dispersed once our CET students start joining, okay, in coming weeks. Therefore, all of you, those who are not able to follow, please let me know. And if you are facing any problem, therefore, we will be continuing with this, and we will be completing the course. In the sense, it is sort of a regular class, the way we used to conduct for others. Okay, and the rest of the whatever the syllabus I have covered so far, if you have any doubts in this, you have to call me back or you have to let me know. Okay, you should let me know where you are facing problem, because these are the important derivations we are in, and these are the important derivations which would help you to score good marks also in our exams. Of course, in the derivations, you should not just concentrate on the mathematical part, physical meaning, and also physics of that, whatever the statements or whatever the diagrams you write, you should inform us, or you should write it in the exam. Then only you can expect marks, okay, or good marks. Okay, do you have any doubt?
Excuse me, sir. It's Miss Shreya.
Yes.
Sir, as I joined yesterday, can you please let me know what are the things I should be covering?
Yeah, because in this, whatever the Microsoft Teams, you are able to log in. Okay.
Yes, sir.
In this particular topic, please go back and look at the videos. Okay.
Yes, sir.
What are the topics which has been covered so far? Okay.
Okay, sir. Thank
Especially,
you, sir.
and those videos won't be available beyond 20 days. You have to download all the videos what has been covered so far, and you have to keep it at your custody. Okay. And initial
Yes, sir.
days, prior to that, you can always take it from your friends, whatever the videos. And if you have any doubts at any point, you can always contact us. Okay. We will help
Yes,
you
sir. Thank you.
solve the problem. Okay. Okay. Now, this is, as I mentioned, that this is one of the important discussions or one of important derivations. Okay, you should pay attention here. What we are trying to do here is restoring forces in a bent beam. What do you mean by restoring force? For example, if I take a pen and if I bend it, okay, whenever I bend it, why does it not break? Because within the material, okay, whenever I take a pen and if I start bending it, then it follows a curved path. Okay, but it doesn't break. Why does it not break? Because there are restoring force acting in the opposite direction. Though my forces are acting in this direction, restoring forces are acting in the opposite direction, make them still intact of the entire body. Okay, that is what the general meaning of restoring forces. Let us try to take this beam and we will try to pull this beam at one end, and let us assume that another end is fixed to a solid support. And then whenever we are happening, or this is one case, the another case is I am applying, whenever it bends, what does it happen realistically is that this outer layer, whatever the outer layer we are considering, okay, from that point onwards, okay, some portions start elongating and some portions of the beam, okay, they start contracting. Okay, that elongation and contractions are bound to happen whenever the given body is under stress. Okay, and that whatever the extra force by which I am making this beam to bend, okay, that will be counterbalanced by the corresponding bending couple. Whatever I am applying here, that should be balanced by another equal and opposite couple what is getting generated here. The moment of this couple, the moment of this elastic couple, we call it as internal bending moment. Okay, this is whatever is getting tracked, or whatever the force or moment of this elastic couple, okay, or what we call it as internal bending moment. This is the property of the given body which makes the given body to be intact under the influence of external forces. Okay, and let us consider a little elongated or a little more detail. Okay, let us consider the beam. Assume that the whenever we bend a pen or anything, let us assume that there is a central layer which is not at all getting affected because of the extra force what we are applying either this side or this side. Okay, let us consider a filament P dash Q dash. Okay, from the neutral axis, let us consider another filament which is above that. I think we already discussed about this in the last class. I'm just reiterating, that's why I'm going little fast here. Okay, I'm considering new element P dash Q dash at a distance x. Okay, and the length of the filament in the unstrained condition is same as PQ. That means that P dash Q dash is equivalent to PQ whenever there is no extra force. But because of the extra force, P dash Q dash got elongated or it got strained. Okay, now let us see that how much the length, extra length it got, or how much it got elongated due to external force. Okay, and the original length is PQ is equal to r theta. We already know that arc length is given by radius of that arc. Okay, and what is the angle subtended with respect to another reference point. Therefore, PQ is given by r theta, and in the similar analogous fashion, okay, P dash Q dash is given by r plus extra x. Okay, this x came from here. Okay, PR plus x into theta. Now the increase or change in length because of the extra force is given by x into theta. Guys, all of you are able to recollect these discussions what we had couple of days ago? Yes, guys. Okay, then we are talking about what is the linear strain getting developed within the body. Okay, that linear strain is given by, okay, change in length to the original length. Okay, increase in length or change in length is given by x theta, and original length is given by r theta. Then these theta I can cancel them each other, and then I am having the expression for linear strain now, x by big R. Now, in our earlier classes, we defined about the Young's modulus, and the general notation for Young's modulus is YRQ. And those who joined late, okay, all these or most of these PPTs in different form are already available in our teams, and notes are also available. Okay, and all our laboratory videos are also available in our in the sense link is available in our notes. Okay, those notes can be accessed in our teams under our engineering physics section under files. Okay, you can please go and watch them. Okay, now linear strain. Okay, I am just recollecting, that's why we are not spending much time here. We have reviewed about these different moduli of elasticity in the earlier classes. Therefore, linear strain or Young's modulus is defined as, if Q is the Young's modulus, okay, then Young's modulus is given by linear stress to linear strain. Okay, in place of linear, we would have taken longitudinal stress also. Therefore, it is stress by strain. Now, the stress can be written as Q times linear strain. Therefore, what is the stress acting on P dash Q dash can be written as, if Q is the Young's modulus representation. Therefore, P dash stress on P dash Q dash is given by Young's modulus, product of Young's modulus and linear strain. Therefore, that linear strain we just got the expression. Therefore, it is given by Q into X by R. Guys, all of you are able to follow up to this point? Hello? Guys? Hello? Hello? Murali Krishna? Are you able to follow? Murali Krishna? Hello? Drulal? 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 Nidhi? Nidhi? Can you hear me?
Yes, sir.
Yeah. Can you please, are you able to follow? Drulal?
Yes, sir.
Yeah. Can you please show your notes? Yes, Drulal, show your notes. All of you keep your notes ready. Manish, Manish, hello, Manish, Manish, can you hear me? Nikhil,
Hello, sir.
hello, Nikhil. Yeah, can you hear me?
Yes, sir.
Yeah, are you able to follow?
Yes, sir.
Can you please show me your notes?
Calculation of pending moment.
Yeah, whatever last class notes and today's notes, can you show me?
Can I see?
Yes, I can see that. Okay, you are able to follow, right?
Yes, sir.
Okay, thank you. Thank you, Nikhil. Deepa, Shreyas, okay, how many of you have left? Let me make sure that in the attendance it is reflected. Deepanjali, Shreya,
Yes, sir.
Dhruv, yeah, are you able to follow?
Yes, sir.
Yeah, can you please show me your notes? Drulal, make sure your notes are ready. Drulal, Drulal, are you there? Shreya, I hope you are able to follow, right? What we had the discussions in the last class also.
Sir, I've started to view the previous videos from today, sir. So I'm still
Oh,
covering up.
okay, okay then, no issues. Okay, thank you. Drulal, Manish, and Murli Krishna. Who is showing now?
Krishna sir.
Huh?
Murli Krishna sir.
Murli Krishna. Yeah, Murli, you are able to follow, right? My major concern is, are you guys following or not? That's my major concern. Hmm? Murli, I am seeing that you are writing notes. I am just asking, are you getting the points also? Whatever we are discussing. I think your audio not very much visible. Okay, and then up to this point, you guys are not having any issues to follow, right? Can we continue?
Yes, sir.
Okay, now basically we got up to this point. Then here, once we got the expression for stress, okay, how do we define stress? Stress is defined as force per unit area. This linear stress is given by, sorry, force per unit area of cross section. Let us assume that there is a notation for cross sectional area as A. Okay, this is area of cross section. As I mentioned in the last class, please don't get confused with this A and the neutral axis representation AB. Okay, this is the neutral axis representation. Okay, where here whatever we are writing A is the area, this is area of cross section. Therefore, stress is given by force per unit area. Therefore, LHS I am substituting it as F by A, and RHS we have QX by R. Okay, now let us consider the same point. If F is the force which produces the stress, then that stress is given by force per unit area, and right hand side we just got the relation where A is the cross section. Okay, and please remember this, whatever A I am considering right now, it is the cross section of the beam. Okay, cross section of the beam. Okay, therefore the force which produces the stress is given by, just simplification of this relation, F is equal to Q into AX by R. Okay, I hope all of you are able to write down, because this has been already discussed in the last class. Okay, now we got the expression for force. Now I want to measure this, what is the movement of this force. Okay, now we got the elongation on a filament, what we have considered a P dash Q dash. Now, okay, we got that what is the force acting on this particular filament. I want to find out what is the movement of this force along the neutral axis. Okay, force is acting on this layer, what we had considered for time being. Now I want to understand what is the movement of this force along the neutral axis. Therefore, movement is given by, or moment of the force is given by force into perpendicular distance from the reference point to the given point. Therefore, the distance is x from the neutral axis and F is the force acting on the filament B dash and Q dash. Okay. Hope all of you are able to follow this step. This is very important step. That's why I am reiterating. Now that is given by same expression f I am multiplying with x, therefore x becomes x square and all other parameters remain as it is. Okay, then now we got the expression for movement of these forces, but we have to understand that I have to understand what is the net moment of the force acting on neutral axis due to all such segments which are available at different distances from the reference point. Therefore, the net moment of the force. Okay, the sum of the moments of all such internal elastic forces acting over the whole cross section of the beam, we call it as bending moment. Okay, the effective bending moment of the beam is sum of such moments of all such internal elastic forces acting over the entire cross section of a given beam, that we call it as bending moment. And hence the bending moment can be written as summation of all these terms. Okay, summation of all these terms meaning, okay, we know that Q is the Young's modulus of the given material of the beam, therefore that is constant, and R is the sort of the radius of the curvature it could have formed due to the application of the forces. Therefore, that is also constant because of the particular weight. Okay, this R remains constant. That R also we can take it out. Now I am left with summation of A into x square. A is the cross section and x is one of the representative filaments position with respect to neutral axis. Therefore, the bending moment is the sum of all such movement of those forces. Okay, that's why we have written this formula. Guys, are you able to follow up to this point? Hello?
Yes, sir.
Okay, therefore, I am replacing this summation of a square, a into x square into another parameter I. Therefore, I am writing a standard definition for bending moment, or standard mathematical expression for bending moment is given by q into I divided by r, where I represent summation of a into x square is the geometric moment of inertia. Please remember that we are talking about moment of inertia in a while, or what you have studied in your lower classes also. Okay, here this definition, geometric moment of inertia is the summation of A into x square, okay, of the cross section of the beam about an axis passing through the center. Okay, this is the geometric moment of inertia of the cross section of the beam about an axis passing through the center and perpendicular to the plane of the bending. Okay, I am considering about geometric moment of inertia. I don't want to mess up it right now. Okay, please write down this definition. Okay, we will explain this in detail in the next slide or subsequent classes. Okay, where I is equal to summation of ax square is called the geometric moment of inertia. Please highlight this geometric moment of inertia of the cross section of the beam, and whenever we are talking about the moment of inertia, we have to talk about a particular axis. Okay, and that axis, whatever I have considered, is passing through the center and perpendicular to the plane of bending. Okay, now we got the expression for I, geometric moment of inertia also. Now let us try to get a mathematical expression for the total moment of that forces. Okay, just now we got the expression bending moment is given by q into I by r. I is the geometric moment of inertia, and that is given by whatever we wrote it, it is summation of a into x square, we just defined it, that can be written as a into k square, okay, where this I represents geometric moment of inertia and k is called the radius of gyration. Okay, we have introduced a new term k, small k, that corresponding to radius of gyration, and a corresponding to, as we already know, that area of cross section, and in this expression q represents Young's modulus, and the denominator term r represents the radius of curvature of the part of the neutral axis. That is, we already defined it. Okay, if you make a circle out of that neutral axis, okay, what is the radius it can subtend over that, that corresponding to r, okay, and k is the radius of gyration. Okay, this is sort of a new term we are going to discuss in detail. Okay, now the bending moment we got in terms of radius of gyration. Okay, now let us try to have this radius of gyration and a case, this entire geometric moment of inertia, we are going to rewrite it once again. Okay, basically now we are restricting this general formula to different shapes of the beam. Now let us consider a rectangular cross section beam. Okay, it is having a rectangular beam. Okay, for that the bending moment is given by q into I by r, and q is equal to a k square by r. This is the standard definition what we are having. Now for rectangular cross section, what is the area of cross section? Breadth into thickness. Okay, this particular cross section if I want to consider, okay, it depends on what is the breadth and what is the thickness. Okay, now we got the area of cross section for that, and the radius of gyration for that material is given by d square by 12. And here we directly take this notation, we are not going to derive what is the radius of gyration value or square of the radius of gyration is given by d square by 12. We are not going to do any derivations here. Okay, we directly take this notation. Okay, directly assume it, in the exam also you can take it directly. Okay, now for rectangular beam we got the expression for k square, and it is straightforward for us to assume that this area of cross section is given by breadth into thickness. We will just substitute in this particular formula, and we get that bending moment of the rectangular beam is given by q into, here whatever we are doing, q we are writing, r we are writing in place of a, it is b into d, and k square is given by d square by 12. Therefore d became dq, q as it is, and b as it is, d cube divided by 12 into r. Now bending moment for a rectangular beam is given by q b d cube by 12r. Guys, are you able to follow? Here we are not going to derive this as part of your syllabus. Okay, we are not going to derive this. Okay guys, are you able to follow up to this point?
Yes, sir.
Okay, and similarly we will do it for rectangular cross section. Okay, and for the rectangular cross section same formula is valid, and we know that for rectangular cross section, okay, this is this is circular shape, therefore the cross sectional area, the circle is given by pi r square, therefore we are substituting a value as pi r square, and radius of gyration for the same circular cross section is given by r square by 4. Okay, again in the exam also you can directly write it the way it is given. Therefore we just substitute these two, then bending moment for a circular cross section is given by q pi r square divided by 4r. Okay, and I hope you are, sorry, r to the power of 4. What is happening here? If you want to write that, q by r, a is given by pi into r square, and k square is given by r square by 4. Then r square and r square became r to the power of 4, q as it is and pi as it is. Then bending moment for circular cross section is pi r to the power of 4 by r. Okay, now in summary, what we are writing, we understood that bending moment depends on Young's modulus, geometric moment of inertia, and radius of geometric moment of inertia and radius it forms, and this is the general definition for that. And Young's modulus of the wire can be determined by calculating the bending moment. That's what we are going to do it in a while in the next class. Therefore, bending moment for a rectangular beam, whenever we consider a rectangular beam, and if Q is the Young's modulus, then that simplified formula is given by QBDQ by 12R, and bending moment for circular cross section, I think I have given it 2 times, is given by pi r square, pi q pi r to the power of 4 by 4r. Okay guys, do you have any questions before we adjourn for the day? Hello guys,
No,
do you
sir.
have any? Okay, if there is the case,